Okay, so this is 15.3 continued. So a vector field big F is called conservative when there exists a differentiable small f such that the gradient of small f is equal to big F. We call a small f the potential function for big F. By theorem 14, a conservative vector field has a property then that line integrals are path independent. That means then the choice of any path between 2 points does not change the value of the integral. So let me draw a picture to explain this better. Let me just let you look at this again before I move on. Okay, so let me explain this conservative thing a bit more. So again, it's path independent. So it means then, say we were 2 points here, I could go to the first one, say like that or something. Call that C1, and this one over here I could go like this. Same one around that way. That's C2. So being path independent would mean then that the line integral over C1 dot dr would equal the line integral over C2 dot dr. That's what it means to be path independent. So all that matters is your starting and ending point. It doesn't matter how you got there. The line integral will be the same. So you can C1 is more direct, I guess. Well, you can even have a C3, say, going a straight line, say. That would also equal this. So be C3. So all line integrals would equal that have the same starting and ending points with the same orientations anyway. If they switch orientations, they differ by a minus sign. So that's what it means to be path independent. Okay, so let's do an example now. This is from the practice quiz. Okay, so this is practice quiz 8, number 1. Show that the vector field is conservative, then calculate the work done by F on an object moving along a curve from 1, 0, 0 to 1, 1, 7. And here's our F down here. So when I show it's conservative, it means it's going to be the gradient of some small f. So in particular then, this guy here would be small f derivative with respect to x. This is small f. This would be small f derivative with respect to y. This would be small f derivative with respect to z. Okay, so note. So small f derivative with respect to x is equal to this guy. Then, so integrating both sides with respect to x, so integrating this guy just become f, and then integrating this with respect to x. Okay, so integrating y squared z, they're constants with respect to x, would be y squared zx. So it'd be y squared zx. And integrating this, you could do use substitution, but it's going to be I'll let you check, it'll be ln of x plus y. And now, to be careful now, it's going to be plus a constant. But here, we're thinking of y and z as constants. So the constant here would actually be a function of y and z. So let's call it maybe cx, y, z. This guy here will be a function of y and z. Okay, so we know our small f should look like this. We have some freedom over what we can choose for this constant. It's a function of y and z. Next, Now fy is going to equal this guy, so I have fy equal to 2xy z plus 1 over x plus y. So then here, so integrating both sides with respect to y, so integrating this side will just become f. So that'll be integral up to x, y, z plus 1 over x plus y dy. Okay, so integrating this with respect to y now. So integrating y will be y squared over 2, we'll cross off of that one, so it'll be x, y squared z, and this will be ln of x plus y, and then you'll have a constant, but here now the constant will be a function of x and z. Call it say c subscript y of x and z. So this now is a function of x and z. Okay, and lastly here, we'll have our, we'll have our fz guy equals x y squared. So integrating both sides with respect to z now, so we'll have our f will be integral of x y squared with respect to z. So integrating this, these are constants, so it'll be just x y squared z plus now some constant. The constant here would be a function of x and y. We call it c z of x and y. Okay, so now let's look at what we have here. So now looking at, we have f three different ways. We have f equal to this up to a constant. We have f equal to this up to a constant. We have f equal to this up to a constant. So notice they all share the x, y squared z, because you can write this x, y squared z there. So that has it, and that has it. Okay, now the first two have the ln's. The third one doesn't. But I have freedom to choose my constant here to be a function of x and y, so I can choose this to equal ln of x plus y. Then all three would have that, and then I can just choose these to be 0 then. I can choose that to be 0, and I can choose that to be 0. Doing that, then we'll be able to find our small f. So let me erase some things and let's keep going. Okay, so now we've identified our f. Let me write my f over here, then the small f. So we said it's going to be x, y squared z plus ln of x plus y. Okay, so we got that now, and now I guess we don't need this stuff over here anymore. So let's erase this. So by design then, so by design, we'll have that big F, you can check will be just the gradient of small f, where small f is this. So therefore, that's definition of conservative. And also by theorem 14, we know it's going to be path independent. So here it tells us the start point and end point. It doesn't tell us the curve in between them. It doesn't matter what the curve is. So by theorem 14, we'll have the integral over C, our curve, from this guy to this guy, f dr. Will this be my small f evaluated at the end point. So 1, 1, 7 minus small f evaluated at the start point. So we've proven in Theorem 14 that this is true. And my small f is over here. So we'll just plug in those values and get our answer. So let's do that. So plugging in here, so plugging into this guy up here. So x is 1, y is 1, z is 7, so it'll be 1 times 1 squared times 7 plus ln of x plus y, so it'll be 1 plus 1, then minus, as now putting 1 in place of x, 0 in place of y, so it'll be then 0 for this guy, plus ln of 1, but ln of 1 is 0, so let's get then 7 plus natural log of 2. So that'd be your answer. Okay, so we're done.